We're going to continue with our magnetostatics as we move into Chapter 8 in the textbook, and the first topic of many that is covered in Chapter 8 is magnetic forces. And so it turns out that there are three ways in which force due to a magnetic field can be experienced. And so in this video, we're going to take a look at the first one, and in subsequent videos, we're going to look at the other two. So the first way that we can experience a force from a magnetic field is if it's a force on a charged particle that is moving in that magnetic field. So force on a charged particle moving in our magnetic field. And so I'm just going to write B, and so this is the same B that we had referred to as our magnetic flux density previously, and so we're also going to use that to describe our magnetic field in general. So of course a key thing here is that our charged particle needs to be moving in order to experience any force. And so experimentally we have an equation for this. So experimentally it has been determined that our magnetic force, F sub m, which of course is a vector quantity, is equal to Q, which is the charge on our particle, times U, which is our particle velocity, cross with our magnetic field. So this is going to be our magnetic force on some charged particle. Again, it has to be moving, so this is our particle velocity. And so there are a few things that we can point out about this magnetic force based on the form of this equation. So as I pointed out a couple times now, our F sub m is only going to be non-zero if we have some moving particle. So only non-zero for moving charges. So if all the charges are stationary, they're not going to experience any force. And so that's of course because this whole first term here would go to zero. The other thing that we can notice is that our Fm, the force, is perpendicular to the velocity and the magnetic field. So Fm is perpendicular to our velocity and our magnetic field. And so that's just due to the definition of cross product. And so what that then tells us is that our Fm is also going to be perpendicular to our dl. So if it's perpendicular to our u, then it's also perpendicular to our differential length, so the path along which our charge is moving. And so ultimately what that means is that this magnetic force cannot perform any work. So cannot perform work on the charged particle. And another way that we could state that is it can't change the kinetic energy of the particle. So it's essentially changing the direction it's moving in. So cannot change kinetic energy of our particle. So we can contrast this magnetic force on a moving charged particle to our electric force that we talked about previously. So let's now go back and sort of review for a second our electric force. So previously we had just called this F, but now let's put a subscript E to indicate that we're talking about electric force. And so that was simply equal to Q times our electric field intensity E. And so of course in this case we don't have any stipulation that our charge has to be moving. So this charge can be moving or stationary. So charge can be moving or stationary, so no restriction like we have with our magnetic force. This electric force can also perform work, unlike our magnetic force. So it doesn't necessarily perform work, but it can perform work. And so of course what we can do is we can combine these two force equations into a single force equation. So we have our electric force equation here. Try not to cut off the F there. And we have our magnetic force equation up here. We can combine these into two if we have the presence of both a magnetic and an electric field. So let's say in the presence of B and E, of course we're going to have both of these, and our total force is given by something called our Lorentz force equation. So total force given by our Lorentz force equation. And so really all it is pretty simple. We're just going to write the two together. So we can say the overall force is equal to the sum of the two forces, so the force from our electric field plus the force from our magnetic field, and this is equal to, and now both of those equations had a q, so we can factor out the q, and that's going to be multiplied by the quantity of our electric field intensity plus our particle velocity crossed with our magnetic field. And so this is our general force equation for a particle in the presence of an electric or a magnetic field. And so of course what we can see is if we had zero magnetic field, this term here is going to go to zero. If we have zero velocity, that term goes to zero. If we have zero electric field, this term goes to zero. So we can kind of use this more generally in all cases, but of course we don't need to have this full equation if we only have an electric field or if we only have a magnetic field. Another thing to note, which we'll see a little bit later on in some examples, is that typically our magnetic force is going to be small compared to our electric force. So typically our F sub m is going to be small compared to our F sub e. Of course, the one exception is going to be as this velocity term gets higher. Now, of course, there are obviously other exceptions. In some cases, we might have really high magnetic field with lower relative electric field. But generally what we're going to see is that our Fm is getting more comparable to Fe when we have higher velocities. So maybe not just the one exception, but let's say the main exception that we encounter is going to be large particle velocity u.